Good morning to everyone. My name is Guido Saccone and I am a research engineer of the Italian Aerospace Research Center. This presentation is dedicated to the kinetic assessment, CFD modeling, and experimental validation of hydrogen combustion, especially conceived to supersonic air-breathing scramjet engines. These activities were carried out in the framework of the STRATOFLY project co-funded by the European Commission under Horizon 2020 program and pursued by a consortium of several European academic and research institutions, including Chile, and led by Politecnico di Torino, aimed to improve the technology readiness level of high-speed passenger stratospheric flight by means of a multidisciplinary optimization approach, and a special care was paid on minimization of both chemical and noise emissions, ensuring at the same time elevated standards of safety. In this chart, the main characteristics of the STRATOFLY vehicle are summarized. It is important to highlight that the fuel is only liquid hydrogen, so no carbon-based emissions are released, and especially carbon dioxide, and also NOx emissions were minimized. The propulsive system consists in 6 air-tube rocket engines and 1 dual-mode ramjet. Hydrogen is estimated to be a clean fuel, since the overall product of its complete oxy-combustion is only water, even if, when it reacts with air, also NOx are produced due to the reachment of very elevated flame temperature. In any case, supersonic hydrogen combustion is a very challenging process involving several complex chemical-physical phenomena, and the operation of a scramjet is further complicated by the very short residence time of the flow within the thrust chamber, that is of the same order of magnitude of the chemical kinetic ignition time. Since experimental measurements is often unfeasible, design and development of scramjet engines often relies on CFD modeling, and hydrogen-air combustion and chemical kinetic assessment is the first fundamental step. For this purpose, several zero-dimensional kinetic simulations were performed using the open-source Cantero tool under Python interface, simulating homogeneous isochoric batch reactors and solving the fundamental matter and energy balance equation using 3 different kinetic mechanisms. The first one was the JACHIMOWSKI 1988 scheme developed by the NASA Langley Research Center to describe the hydrogen-air combustion up to Mach 25 speed in scramjet operations, and further improved by means of comparison with experimental data in terms of ignition delay times and laminar flame speeds. It was demonstrated that the scheme is very sensitive to the rate coefficients of the 2 most important reactions highlighted in red on the slide, and also the addition of NOx to the initial reacting mixture was investigated, and the influence of this addition on ignition delay times was studied because nitrogen monoxide can produce radical OH that is of fundamental importance because it is the flame marker. The other investigated mechanism was the Kelvin 2013, originally designed to study the combustion of a single mixture up to 70 bar and over the wide temperature range in both fuel-in and fuel-rich conditions, including also the extracted radical OH species, and the authors demonstrated that the reactivity and ignition of hydrogen is mainly controlled by the competition between the chain branching and the pressure-dependent chain propagating reactions. And at a low temperature, below 1000 Kelvin, the ignition is primarily controlled by the reaction R9, and the chemical path consisting in formation of hydroperoxyl and oxygenated water chemical species becomes very important, while at a more elevated temperature, greater than 1100 Kelvin, that are the temperature most representative of shock tube experiments, the competition is dominated by the reaction R1, and in any case, the ignition of hydrogen is very sensitive on the operative pressure. The third investigated mechanism was the Z25, developed by the Swedish Defense and Research Agency, starting from an original mechanism consisting in 22 irreversible steps, plus the 3 fundamental Zeldovich nitrogen monoxide generation reactions, and especially designed, optimized, and improved to achieve a very good agreement between the ignition delay times predicting using this scheme and experimental data in a particular connecting critical zone denominated crossover region and identified in the temperature range between 900 and 1100 Kelvin. That is exactly the operative box in which several Ramjet, Scramjet, and dual-mode engines operate, studying the competition between the chain branching and chain propagating reactions, and demonstrating also that the reaction R17 plays a very important role in consisting in a thermomolecular decomposition of oxygenated water, leading to formation of the OH radicals that are fundamental frame markers promoting the chain explosion. First of all, there's a mechanism where kinetically assessed by means of comparison between the predicted ignition delay times values using the same initial conditions in terms of temperature, pressure, and equivalent insulation, and experimental data measured in both shock tube and rapid compression machine test rigs. As you can see from the plots, while at a low pressure up to tube bar, almost all the 3 investigated mechanisms provide a very good agreement with experimental data, increasing the pressure, and especially in fuel-in conditions, only the Z25 scheme exhibits a very good behavior, while the other mechanisms are very far from the experimental data. This trend was also confirmed considering other experimental datasets. So it is possible to conclude that the best agreement was achieved by the Z25 kinetic mechanism, at least on a zero-dimensional chemical kinetic point of view. That is the only mechanism able to reliably describe the combustion process and ignition phenomena in the crossover region and above tube bar of pressure, while the JACHIMOWSKI and Kinetic mechanism show a satisfactory behavior only at high temperature and low pressure conditions. Then there's a chemical mechanism we have implemented in ANSYS Fluent software to simulate in reacting fluid dynamic real fluid 3D conditions simulations, and in these plots the temperature distribution in the engine were reported in terms of isosurfaces of 20% mass fraction. These are the solution obtained using the JACHIMOWSKI reduced mechanism with both laminar finite rate and the dissipation model as combustion approaches, and standard K-epsilon turbulence modeling, and the second order upwind discretization scheme. Finally, the experimental validation of this chemical and fluid dynamic model was confirmed by means of rebuilding of the ground-based testing carried out in the German Aerospace Center DLR, removing the intake, so considering only the combustion process and the nozzle expansion, starting with an inlet temperature greater than 1100 Kelvin, and O2, the unexpected compression and the shift of the pressure profile between the computational and experimental values, the peak pressure determined using both the JACHIMOWSKI reduced and the Z25 kinetic mechanism, having good agreement with the experimental measurements, confirming that in these conditions, at an inlet temperature greater than 1100 Kelvin, both the kinetic mechanisms are reliable in prediction of hydrogen-oxygen combustion. So in conclusion, we have studied the hydrogen supersonic combustion on both chemical kinetic and fluid dynamic points of view, and an assessment of the best suitable and the most suitable kinetic mechanism able to reliably describe the Scramjet engine's operation were performed, and fully three-dimensional CFD simulations confirmed that both the kinetic scheme due to Zetterberg and JACHIMOWSKI at inlet temperature above 1100 Kelvin are feasible and reliable in the pressure predictions, and the comparison with the experimental data is promising. Thank you for your attention. Any questions are very welcome.